So next, I'd like to hand it off to Bjorn Flatt, who's the head of emerging technologies, and he will talk about really the foundational layer of this full stack, which is our hardware. So thanks, Bjorn.
Thank you, Masako. My name is Bjorn Flatt, and I lead the emerging technologies team here at IonQ. I'd like to take the next couple of minutes or next few minutes to talk about connected systems. In connected systems, we have actually several understandings for that. One, we just acquired Qubitekkinisu를, a quantum networking company. So connected system is clearly something we think about in the means of quantum communication. But it's also a way for us to scale our systems, to connect our QPUs, our ion traps to each other. And one step is shown on the next slide. It's kind of to come up with a modular architecture for our systems. In an earlier webinar in this past summer, we talked about our compact vacuum packages we're working on, and that we were in the process of completing our UHV assembly chamber for prototype development. In this video on the right-hand side, you see that chamber, which has been completed in our facility in Seattle and is about to go into operation. This chamber allows us to produce hermetically sealed trap packages. These packages will eliminate the need for mechanical pumps, drastically reducing the form factor and the volume of our vacuum systems. By removing mechanical parts, it will also increase the robustness and reliability of our IonQ systems, taking another step towards enterprise-grade capability. On the next slide, we see that we also designed our compact vacuum packages. In the graphic on the right-hand side, you see the comparison of the current package next to a quarter and compared to the first generation vacuum package we used in earlier systems. So that's about a reduction in size of more than an order of magnitude. This reduction in size, weight, leads also to a reduction in power consumption. We do not have to power all these big vacuum pumps required there. Again, as a reminder, vacuum is important for us because our inherently pure qubits on the atomic base need to be isolated from environmental influences, and that's what we do in the trap package, in the vacuum package. Again, having these smaller, more compact packages allows us to accelerate the manufacturability, the installation, and the maintenance of our systems. Another advantage of these packages is shown on the next slide, where we point out that we can actually operate these packages at room temperature. And that is a huge reduction in the operational cost. If you compare that on the right-hand side, superconducting qubits, for example, operate at the tens of millikelvin range. If we can operate these at room temperature for our systems, we do not require cryostats. Again, an additional reduction in cost, size, and weight. Also, we do not need coolants like liquid helium. That again is a step towards sustainability and manufacturability at scale. Overall, this approach for the compact modular systems, together with interconnecting those packages, we have integrated photonics, which we addressed in a blog post about 2 months ago, are significant steps towards our three-pillar technology strategy for delivering performant, scalable, enterprise-grade systems. With this, thank you very much, and back to Margaret.
So this last slide wanted to just wrap up and talk about the summary of what we talked about today. At the core of what IonQ has been doing since the first of our building of our first computers, Harmony, and now Aria, which is our current quantum computer, Forte, which has been available in AWS announced, Forte Enterprise, Tempo, and Future Systems. And as Bjorn just talked about, we have to connect these systems because a really key part about scaling quantum as well as classical, to be honest, is connecting. A computer by itself is lonely. It's got no one to talk to, and it has no capability of getting bigger and bigger and stronger and more scalable without it being connected. There's also another notion of networking and connectivity in what we're doing with Qubitech, as far as getting a stack that relies on hardware, software, and applications that then can actually be expanded and used in the more classical term of networking, being able to go across a network. We did talk about our IonQ quantum software. It's an area that we hadn't talked that much about previously, but obviously, as with any computing system, we did need an operating system. We need the SDKs, we need the APIs, we need to be able to allow applications to be running on the stack that is both the hardware and the software. Coleman talked in depth about hybrid services, very much like other areas when we used to talk about how do you get on-premises servers to actually communicate and work with other types of servers, let's say on the cloud. We talked about hybrid, about being on-premise, hybrid in the cloud. In quantum, we have the same thing. How do we make sure that we're working with classical, working with companies like NVIDIA to make the ability to have quantum and classical work seamlessly together and be optimized to actually work so that any developer can easily use our stack? And then finally, on the very top, computers and software mean nothing if there aren't applications that have real outcomes and real impact. Back to our mission statement, they're very complex problems that Masako talked about, complex problems that can save lives, that can change the world. We have to make sure that we have a robust applications team that's able to actually address some of the largest, most difficult problems with quantum algorithms that they're building. So that is IonQ's full stack quantum innovation. We're very excited about the stack that we have been building over the years, and we have a lot more exciting things to come.